Okay, so today we will discuss about BJT characteristics. So please write down. When we say characteristics, we mean IV characteristics, current versus voltage. All right. Now, in BJT characteristics, we have two types of characteristics: input characteristics and output characteristics. So, in input characteristics, it is versus uh, input current versus input voltage at output voltage constant. Input current versus input voltage at output voltage constant. Output characteristics is output current versus output voltage at input current constant. Sorry, this is input I slash P. You all write the full form, please. Okay. So BJT has two types of characteristics, input and output. Now, how many configurations we have for the BJT? Yesterday we talked about the configurations. So what are the BJT configurations? Tell me. There are three configurations. Common emitter, right? Common base and common collector. So each of them will have input characteristics, output characteristics, input characteristics, output characteristics, and again. So how many characteristics we have to in total? 6. Okay. For common emitter, common base, common collector, we have to draw input and output characteristics. Right now, you draw just characteristics. In some time, I'll explain you how we got that characteristics. Okay. Can we start with common emitter? Okay. So write down common emitter configuration. I'm writing short form. Common emitter characteristics. Okay. In common emitter configuration, first of all, let me draw. I'm drawing a very rudimentary picture, very rude picture. Actual will involve some resistors also. So this is my BJT. Where is my base? This is my base terminal. This is my collector terminal, and this is my emitter terminal. Now in common emitter is common between input and output. This is my input. This from here to here, and this is my output. Understood? Now, tell me for input characteristics. Now I want to plot input characteristics. Please draw this diagram along. And now I will draw input characteristics. I'm writing short form. What did I tell you for input characteristics? Input current versus input voltage, right? So what is my input current over here? IB. So I'm marking in black. IB is my input current. And what is my voltage? VBE. Here. Positive, negative, VBE. Let me draw it a little bit more neatly. So this is VBE. And this is current IB. And this is my input. So it will be a characteristics between IB versus VB at what constant? Can you tell me? At output voltage constant. And what is the output voltage? VC. What is the output current? IC. So first of all, write down IB is the input current. Write down this please. VBE is my input voltage. What is VCE? Can you tell me? Output voltage. IC output current. Please write this down with this diagram. Is this clear? Okay. VB is my input voltage. IB is my input current. VC is my output voltage. IC is my output current. So what is input characteristics? Input current versus input voltage at constant output voltage. And what is the constant output voltage? At VC constant. Yes or no? Understood? Now basically base emitter junction in active region, it's basically acting as a PN junction, right? You know, we have a N, P, N, and this is my emitter, this is my base. Normally we forward bias the base emitter junction and it behaves as a PN junction, right? So the characteristics will be, now what will come where? When I write, whatever I write first will come in the x-axis, y-axis, and whatever I write next will come in the x-axis. So it will be IB, which is on the y-axis, versus VBE. Understand this, this is also very, very important. And what I told you, it's like a PN junction, right? Base emitter, you apply the supply voltage, which is forward bias, and you will get a characteristics which is looking like this. See, exponential. It's like a PN junction, right? So it's exponential in nature. And for different value of VC, your graph will be like this. I mean, it will be very close to the first one. I'll explain you in some while why it is so. So please draw the characteristics. This is for VCE equal to 10 volt. This is for VC equal to 5 volt. For example, this is my characteristics. IB versus VB for a constant value of VC. This is input characteristics of common emitter configuration. Okay? It's exponential in nature, that's it. Have you drawn? Right now I am just describing how it looks. In short while I'll explain also. Can I go to output characteristics? Okay. Exponential in nature. Very important for your experiment number 8, BJT virtual lab, right? I think you have plotted this characteristics only, input. So this is my input characteristics. Can I go to output characteristics? Okay, tell me, how do we plot output characteristics? Output characteristics is between output voltage and output current, right? So IC versus VC at what constant? See, we have written a definition. At output input current constant. So what is my input current? IB. So at IB constant. And now I will plot the characteristics. IC versus VC at constant IB. So this is how the characteristics look like. Again, remember, current will always come in y-axis. It is IC versus VCE, and the characteristics look something like this. It increases, then it remains constant. It increases, it remains constant. This is how you got, right? And these are for different values. IB1 equal to 10 microamperes, IB2 equal to 20 microamperes. Output characteristics of BJT, explanation coming in some time. First, let me draw all the characteristics. Oh, by the way, I didn't tell you the practical range. Here, VC will go from, let's say, 0 to 10 volt. Here it is 1, 2. Here IC will be in milliamperes. So maybe 0 to 20 milliamperes. Just an example which I'm giving. First characteristics, I didn't give you the range, right? So first complete this, then we'll go to the next one. I'll come back to this in detail, how we are getting these characteristics. So by tomorrow, we will complete BJT module, that is module 5 will be over. Completed? Remember, IC is in milliamperes and VCE is in volts. Now write the range for this also. This is from 0 to let's say 2 volt. That's it. 0 to 2, and IB is in microamperes. Please mention that. So maybe around let's say 100 microamperes. 0 to 100. This is 0 to 2, around 0.1, then so on and so forth. So range is also important. IB is in microamperes, IC is in milliamperes, and both are related by beta. What is beta formula? Beta is the current gain, na? What did we say yesterday? It is IC upon IB. And milli divided by micro will be greater than 100 easily. Okay? Understood about common emitter characteristics? So first you draw this, mark the input and output current, input and output voltage, and then draw the characteristics. Plain and simple. Any difficulty in this? This you thoroughly remember, please. Next, we'll go to common base characteristics. So please write down. Common base configuration. So in common base configuration, the base terminal is common between the input and output. So how you draw that is as follows. You draw the BJT horizontally and mark it like this. So this is my input, this is my output. Acha, which are the terminals? This is emitter terminal where the arrow is. This is base, this is collector. Now tell me what I will write for input current. Can you tell me input current direction outward, IE? And what is my input voltage? VB, right? Yes or no? Acha, what is my output current? IC. And what is my voltage over here? Yeah? VCB. We can write VCB, positive, negative. VB and VCB. So can you write that? IE is the input current, VB is the input voltage, VCB is the output voltage, IC is the output current. Or do I need to write that also? So please write this. IE is the input current, IC is the output current, VBE is the input voltage, and VCB is the output voltage. So this is input output current. Correct? This is input output voltage. Got it? So now tell me, if I plot input characteristics, so which all two I will plot? Input characteristics is between input current and input voltage. So what is input current? IE, right? Versus, tell me, VB at constant VCB, right? Input current versus input voltage at a constant output voltage. Now, let's plot the characteristics. Surprisingly, again, it's a base emitter junction. It is IE versus VP. Again, it is exponential. Oh, sorry. For two different values of VCB, this is VCB equal to 5 volt, VCB equal to 10 volt, constant values, starting from 0. And again, VB will go from 0 to 2 volt. IE will be in milliamperes or microamperes. Can anyone tell me? IE is the highest current, so it will be in milliamperes. So maybe around, let's say, 20 milliamperes, 0 to 20. That's the difference. In input characteristics, IB was microamperes. Here it is milliamperes. So it will increase exponentially. Are you understanding how to draw the characteristics? What will be in the x-axis and y-axis? IE versus VB. Next, let us draw, completed? Let us draw output characteristics of CP configurations, okay? So tell me what is my output characteristics versus output current IC versus in output voltage VCB at a constant input current. So please mark, it will be IC versus, come on, tell me, IC versus VCB at constant IE. And the graph, see, listen here, how you draw it. Everyone listen carefully. This is IC, this is VCB, okay? So you have to extend this graph because it goes negative. See how to draw it. Two parallel lines you draw, okay? And mark over here I equal to, let's say, 2 milliampere, I equal to 1 milliampere. Mark one point over here and then drop the graph to 0. See, like this. Like this. So this is the point actually. Understood? It goes in the negative side. So please draw this characteristics. Basically, output characteristics will tell me whether the BJT is in saturation, cutoff, or active region. Alright. Common collector, well, I'll discuss while I explain the characteristics directly. So I'm not discussing common collector right now because common emitter and common base are more important. Common collector, while explaining only, you can draw the characteristics. Okay. So right now, I'll start with the explanation of common emitter characteristics. So all of you are ready? You have drawn this characteristics. Common emitter, common base, this 4 input, output, draw it very thoroughly. Write the correct voltage and the correct current in the X and Y axis. So now let us start the explanation of, basically what I'm going to explain is why the nature of graph is like the way it is. Alright. So let me start. Common emitter. Okay. Since it's a little bit of a long topic, whatever you feel important, you can write. Okay. Rest you can listen. Now, out of the three, common emitter is the most often used. It's most famous configuration, by the way. Alright. Let me concentrate over here. One is symbolic diagram. That means you use the symbol and then show the connections. One is structural diagram. You draw the structure of the BJT, then connect the supply voltages. Now listen very carefully. For the common emitter configuration, we are using NPN BJT. So, what are the two conditions for it to be in the active region? Base emitter junction should be forward bias and base collector junction should be reverse bias. Yes or no? For active region only. But we are connecting it in such a way that BJT can be in cutoff, saturation and also active region. So here you connect the power supply between base and emitter and another power supply between collector and emitter. Alright. My base and emitter is the input. My collector and emitter is the output. IB is my input current. IC is my output current. Okay. Understood? Now this is the same thing explained in structural diagram in the form of BJT structure, NPN structure, emitter, base, collector. Alright. Which diagram will help you to understand this diagram? So I'll explain you with the help of this diagram. Alright. Now, this I've already explained you. NPN BJT in active region meaning base emitter should be forward bias, base collector should be reverse bias. Now, let's go to the characteristics. I think this is the characteristics, right? Which you have drawn just now. IB versus VB at a constant VC. Okay. Now, let us concentrate on the structure. Forget about collector and emitter. Only concentrate on the base emitter. Okay. Let me highlight this. Only concentrate on the dismal circuit. So if you see carefully, VBE, here we have positive, here we have negative. So it's a PN junction, right? So current flows like in a PN junction forward bias. And how is that? Exponential in nature, right? So that's why you get an exponential graph. Understood this? Now, the thing which I have to explain is why is the graph different for different values of VC, right? Correct? It is for VC10 it is higher, right? Current is little bit on the other side. So for the input characteristics is similar to PN junction characteristics since base emitter junction is forward bias. So if VB increases, IB increases exponentially for a constant VC value. Now, here I go. See what I am doing. This is one point of VB and there are two different current levels. So for which graph current is higher? For same value of VB, which graph current is higher? VC equal to 1, right? So I have to explain why by VC increasing, IB is reducing. IB is reducing now. By increasing VB, IB, this is IB, right? So this IB is reducing. We have to explain that why. Did you understand why it is exponential in nature? Because of the PN junction nature. Okay. Now I have to explain why IB is reducing. So can I say VC is VCB plus VB? No, didn't. Acha. Since VCB can be written as VC minus VB, right? Emitter is common, na? So we can write VCB as VC minus VB since emitter is common terminal. So here only I can write VC is as VCB plus VB. Understood this? Okay. So therefore VB is constant. Why VB is constant? With VB constant. Let's say if my base emitter voltage is constant. If my VC is increasing, VCB will increase. Agree? If this is constant, let me explain you. If this is almost constant, and if I increase the value of VC, can I say VCB is increasing? Yes or no? Because VB is almost constant, 0.6 to 0.7 volts, it varies, but almost constant. Now, if VCB increases, what will happen? What is VCB basically? Are common base collector junction, na? So if VCB increases, your base collector junction will become more reverse bias. Yes or no? And if it becomes more reverse bias, what will happen? See, this is my structure of NP and BJT. So what will happen is this is my N. Okay. Did it got back? Yeah. So this is my N emitter, this is my base, and this is my collector. So what really happens is, let me draw this again. Okay. So these are my NPN regions. Now if I increase the value of VBC, this is my depletion layer, initial depletion layer, okay? Now I'll make base collector junction more reverse bias. So what will happen to depletion layer? It will expand or decrease? Reverse bias, now it will increase. So it will increase like this. So basically what is happening? Effectively, my base width is reducing, right? The base is becoming so small, now base width is this much only. So what will happen? The number of charge carriers in the emitter, I told you 10 lakh, are coming into the base and base region is very small. So very less number of them will recombine. So most of the electrons will go to the collector. Less chances of recombination at the base. So what will increase? So with increase in VCP, that is base collector base junction will become more reverse bias. That is base collector depletion region width will increase. Effective base width reduces from WB to WB dash. That means earlier it was WB, now it increased to WB dash. It reduces. So the possibility of electron hole recombination in the base will reduce. So less number of electrons will recombine because base region has become more thinner. See the yellow portion. Earlier it was full, larger. Now we are increasing the reverse bias between base and collector. So this depletion region will go on increasing. Base width will go on decreasing. So possibility of electron hole recombination in the base will reduce. And what will happen due to that? Most of the electrons traveling from emitter to the base gets collected at the collector. So result क्या होगा? IB reduces. Again, see, less number of electrons are getting recombined means what? IB will reduce. Definitely, right? So that's the reason why if we increase the value of VC, your IB will reduce. Understood this? I've written in words everything, so you need not worry about this. It will go in what I am explaining right now. Understood the justification? Okay. Can we go to the next one? Or you can read all these things. So therefore, VC increases, IB will reduce. Now, from the input characteristics, you determine one parameter of BJT, and that parameter is called as RN, input resistance. How do you determine? Can you take two values of VBC like this? You consider two values of this thing. So this is what? Delta IB. And what is this? Delta VB. So you know resistance is voltage upon current. So change in VB upon change in IB will give me input resistance Rn. So where you have drawn the input characteristics, now just write the formula for Rn at VC constant. It is called as input resistance of BJT in common emitter configuration. It's delta VB upon delta IB. This PDF I have already said. I'll say it again. Okay. Rn is the parameter which can be measured from the input characteristics of BJT. All right? Yeah. Can I go to the output characteristics? See, all this information is new to you. So, I mean, at one go you might not understand. So you have to revise these things on the same day. Can I go to next one now? Yeah. Next is this. Output characteristics is VC versus IC at a constant IB value. And this was the graph, right? This is the graph. Now, in this graph, we have three regions. Can you see the green color region? That is the cutoff region. This yellow color region is my saturation, and where I have written 2 from year to year. Entire red one is my active region. Now, how this comes, I'll explain. You can, refer it later, right? Region number 1, 2, 3. So from the output characteristics, you can determine in which mode BJT is operating, depending upon which characteristics it is. So region number 2 is active, 1 is saturation, 3 is cutoff. Actually, I have shown over here, but this region is almost parallel to the x-axis, very, very small, for IB equal to 0. Okay. Okay with it? 3 regions of operation. Now I'll explain one by one. Now, in active region, listen to active region. Where does the active region start from? Here. This entire rectangular circle I have drawn. Entire inside, whatever is inside is my active region. You understand? So what is happening in active region? Just tell me. As my VC is increasing, my IC is almost increasing. If I increase the value of IB, I get a higher value of IC. That is what observation is, right? Yes or no? Now, as IB increases, IC increases. See, IC is beta times IB. So of course, if beta increases, IC will, if IB increases, beta being constant, IC will also increase. Okay? As VC increases, IC also changes slightly. Now, why this is happening, we'll also explain now. See, as VC increases, IC increase is slightly, correct? It's slightly increasing, right? It's not almost straight line. So please concentrate. I'm only explaining active region. So please concentrate on this. Did you understand if IC increases, if IB increases, IC will increase? Now I'm explaining if VC increases, how does the IC increases slightly? So if VC increases, VC is what? VCB plus VB. We have seen this last time. Okay. VB is almost constant, let's say, being IB being constant. As VC increases, VCB increases. Yes or no? Is this understood to you? Yes. Now, as VCB increases, collector base depletion layer width increases. Okay. I guess I have to stay away from this wire. It came, no? Came now. Okay. Stop. All right. I have to be careful with this wire. HDMI cable. Okay, so where we was, as VCB increases, collector base depletion layer width increases. Same situation, right? So this width is decreasing. So what will happen? Effectively, the base width will reduce. Because of that, what will happen? Less number of carriers will recombine at the base. Most of the carriers in the emitter will travel to the collector region. So IB contribution will reduce because less number of electrons will recombine with the hole in the base region, because base earlier it was this much, now it is reduced. So less number of carriers will recombine. So most of the electron traveling via base will be collected by the collector. Yes or no? Correct? So then therefore IC increases. So if IB is decreasing, if your IB contribution is less, those electrons which were not recombined at the base will travel to the collector. So simple reason is IC will increase slightly, not that much. Maybe it is 1 milliampere, it will become 1.1 milliampere. So therefore as VC increases, IC increases with it slightly. Actually I should write a word over here, slightly. This also I have only written, but still. Okay, and also one more thing, in active region you can use BJT as an amplifier. So that is all about active region. समझ में आया? Active region, understood? Yeah. Now you have written already this, right? IB is the input current, IC is the output current. They are related by IC upon IB. Beta is IC upon IB. If you have not written, please write this down near the output characteristics. DC current gain. Beta, very important. Beta is called as common emitter current gain. I told you yesterday that I'll tell you about alpha also. Alpha is coming up. So beta is IC upon IB. It is beta DC. Beta AC is also there. Delta IC upon delta IB. How do you determine that from the characteristics? This one value of beta IB extended to the y-axis. Another value of IB extended to the y-axis. Here. And then correspondingly IC you will get. So IC upon IB will give you beta. Did you understand? So write down this beta DC and beta AC. Basically, you just remember beta is IC upon IB. Okay. Can I start now further? Yes or no? Now listen to the characteristics. See, can you see the yellow color portion? That is my saturation region. What is noticeable in the yellow color region? If I decrease the voltage, let's say this voltage over here is some value. Let's say it's 0.4 volt. So we see value 0.4 volts. So below 0.4, your what is happening to the current is decreasing rapidly to 0, right? So below 0.4 is decreasing rapidly to 0, and that is my saturation region. Yeah. So listen to the explanation. In the saturation region, as the value of Vc reduces, you see in the saturation region, this is the graph, right? ऐसे ना? This is the yellow region, right? So what is happening? Your Vc is reducing. Vc reducing. So what happens to the current? Current is reducing to 0 rapidly. So why it happens? Let's understand. Vc is Vcb plus Vb. Vb is constant. So if Vc decreases, Vcb decreases along with it. So base collector region becomes lesser reverse bias. And finally, at a very low value of Vc, collector base junction become forward bias. अभी ये कैसे होगा? How this happens? How this will happen? See this. Vc, Vcb, Ve. Let's say this is 10 volt initially. This is 0.7. So how much is this? 9.3. समझ में है ना? Simple max. अरे 10 is equal to 9.3 plus 0.7 ना? Yes or no? Now, so base collector junction will be, what is it? VCB minus 9.3. That's why it is reverse bias, right? समझ में आ रहा है what I'm saying? Yeah. Now, I'll change these numbers. Let's say this has become 0.4 volt. Okay. And ये तो change नहीं होगा. VB is 0.7 only always. What will be this? What should be this? अरे क्या होना चाहिए VCB? Tell me. Correct? It should be minus 0.3. मतलब VBC क्या होगा? VBC base collector junction should be how much? plus 0.3 मतलब ये forward bias हो गया ना. Base collector should be reverse bias, but now at a very low value of BCE, base collector junction is becoming forward bias. Check this. Understood? So whenever both are forward bias, which region of operation we are in? Saturation. We have told na, base emitter, base collector both are forward bias. Then my see this. Here देखो. Saturation में both should be forward bias, right? So whenever I am in saturation region for very low values of VCE, as I have explained over here, this is the equation which you need to remember. This example. VC becomes 0.4, VBC will become very small, and that is forward bias. Okay, that is what is happening. Base emitter is also forward bias, and now base collector region is also becoming forward bias. So what will happen now? As VCB junction becomes forward bias, electrons will not reach the collector. ये क्यों होगा? Why it will happen? Let me explain. So this is my emitter, which is N. This is my base, which is P, and this is my collector, which is again N. Now what I'm saying is, base emitter junction is already forward bias, right? So this is forward bias. And now I've connected this also. Okay. So this is forward bias, this is positive, negative. So electrons will flow from N to P. Okay. Now, what I'm saying is this is collector, this is base, this is emitter. Now what I'm saying, base emitter junction क्या हो गया? Base emitter junction is becoming forward bias ना. So how you connect forward bias? ऐसे ना. Correct? This is not actually connected, but this behaves like this. So base emitter junction is forward bias. This is also forward bias. So होगा क्या? What will happen? See. इधर देखो, ध्यान से देखो. If both are forward bias, what are you over here? Electrons na? Electrons will be repelled by the negative polarity, right? Are yes or no? So no electrons will go over here, and here only we have positive. So electrons will be holes will be attracted towards this. Electrons will be attracted towards this side. It will not go to collector. It will go to the base region. Are you understanding? So that's why your current drastically falls to zero when both are forward bias. समझ में आ रहा है? Did you understand? Because lower one is working. See, it is negative, it is positive. So electrons are going from emitter to base. But base के बाद कहाँ पे जाओगे? It will go towards the base, positive supply. It will not reach the collector. Why it will not reach the collector? It will face the opposition from negative. You know now, like charges repel. So electrons will be repelled back. They will try to go, they will send back. So that's why the current becomes drastically zero. See? तो और कम होता जाएगा तो क्या होगा? देखो, what will happen when the VC becomes zero? Sorry, I have to go again and again. This becomes zero, right? ये क्या हो गया? This is 0.7, right? How much will this will become? Strong forward bias बन गया. When both are strong forward bias, current will be zero. That's why IC is zero for VC equal to zero. See this graph. I don't know how much I could explain, how much you have understood, but this is what happens. So for VC equal to zero, IC is zero. That's the reason in saturation region. Understood? Active and saturation little bit. Okay. Other things you can revise it from the graph. Yes or no? Little bit. That's gone inside. So emitter electrons will not reach the collector. Therefore, IC will be zero as VC is reduced to lower value. BJT operates in saturation region in this manner. Now, see, देखो. What do you notice about the cutoff region? One thing is there which is not matching with what I told you. What is the relation between IC and IB? Beta, right? IC is beta times IB. तो यहाँ पे तो IB zero लिखा है. फिर भी IC is not zero. IC is there ना? X axis, Y axis में देखो. So we have to explain why even if IB is zero, IC is not zero. That is cutoff region. That is what I will explain. Understanding now what I am saying? In spite of IB being zero, why is IC not zero? Why it is a small value? That is what I have to explain. Because by the equation which I told you, IC should be beta times IB. So IC also should be present. I'll tell you why. Okay. So this is what I will explain. NP and BJT operates in the cutoff region even when IB is 0. How is that possible? But your IC is not equal to 0. So is it violating this equation? No, actually no. In reality, what I told you at the start of the lecture, I have not revealed all the information about the leakage current. There is a presence of leakage current also over here. Okay, now I'll explain. See, reverse bias where you know PN junction exhibits leakage current, saturation, reverse saturation current. So when IE is 0, when emitter current is 0, your IC is equal to ICBO, and ICBO is the leakage current. Just listen, don't write anything. So basically what happens is, this equation is not complete. कुछ है यहाँ पे. Something is there. We have to find out what is this factor. Okay, and this is basically the contribution of leakage current only. So when I is 0, leakage current is IC equal to ICBO. Now what is IC given by? I have told you this much equation only, right? But ये leakage current है. So IC is alpha times I, but I is IC plus IB, right? So I've expanded this. Okay. So after expansion, 1 minus alpha I am take on the left hand side. Alright. Then 1 minus alpha I have divided on both the right hand side. So I'll get IC equal to alpha upon 1 minus alpha IB plus 1 upon 1 minus alpha ICBO. So IC alpha upon 1 minus alpha is beta. So it is beta IB plus this factor. So this factor is included now. This is the factor which is missing. I told you IC is beta IB, na? But that is the half reality. True reality is this. It is 1 upon 1 minus alpha times ICBO. Now tell me, in the cutoff region, if IB is 0, is my IC 0? No. And this is the reason why. Correct, no? If my IB is 0 now, is IC 0? No. It is 1 upon 1 minus alpha times ICBO. Understood this? And so in the cutoff region, IC is approximately equal to 1 upon 1 minus alpha. Alright. And if I see carefully, beta is alpha upon 1 minus alpha. So 1 plus beta is 1 upon 1 plus beta. So IC is in the cutoff region 1 plus beta times ICBO. And ICBO is very, very small, multiplied by beta, it becomes negligibly small. So this is the equation of current. This is the reason why current is non-zero even if IB is 0. Okay, this is the value of the leakage current at IB equal to 0. It is also called as ICEO. ICEO is collector to emitter leakage current with base open, and ICBO is collector to base leakage current with emitter open. ICBO and ICEO. So that's how it operates. That is why at IB equal to 0 also IC is not equal to 0. What is IC given by? 1 plus beta times ICB. Okay, so please write down this expression. This expression. ये इधर लिखना साइड में, when IB is equal to 0. Write down this expression. And ICBO and ICEO are the leakage currents. Leakage current क्यों आता है? Because reverse bias होता है ना base and collector region. That's why we have a leakage current. I know it's little bit heavy, but this is as it is, the way it is I have explained. If they ask you explain BJT common emitter characteristics, whatever I have discussed today, you need to explain that in short. First of all, characteristics draw karo, then explain karo. You have a doubt? Okay, yeah, time up. So next time we'll see common base tomorrow, common collector, and then we'll also see the BJT applications in switch form and amplifier form. So I'll stop the lecture today.